Hello guys, welcome to H2O, the A to Z of chemistry. I'm Dr. Ritu Johar, your educator for this course, Chemical Bonding. Today we will begin with lecture 28 from the course, but make sure you watch the previous ones before viewing this one. So into the topic of hybridization, we have learned quite a lot now. We have learned what is hybridization, what are the salient features of hybridization, what are the conditions required for hybridization, and then into the types of hybridization we have learned about sp3, sp2 and sp hybridization in the previous few lectures. We will carry on the discussion further on the types of hybridization, and today in this lecture we start with the hybridization involving d orbitals, wherein in this lecture we will be learning about SP3d hybridization. So before we can actually begin with the discussion on the hybridization involving d orbitals, I would just take you back and revise the introductory lecture on hybridization. There we learned what are the types of orbitals which are going to undergo hybridization. One thing that we learned was that the orbitals which are undergoing hybridizations are the ones which are almost equal in energy. And the other thing we learned about the orbitals involved was that they should be of the valence shell. And in some of the cases we see that the d orbitals of the penultimate shell, they can participate in hybridization. So it is actually now this 2 points which are going to be very important when we are going to discuss the hybridization involving d orbitals. Now, as far as the d orbitals are concerned, one thing again, you have to go back to your atomic structure course, wherein we learned about the energy level diagrams. And there we saw was that the 3d orbitals, they have energy which is higher than the 4s orbitals, right? So they are almost of comparable energy, and the filling in the 3d orbitals is after the filling of the 4s orbitals, right? So of course principle was what you learned. And now, based on this knowledge of ours, what you have to remember is that the energy of the 3d orbitals, this is comparable to the energy of the 3s orbitals as well as the 3p orbitals. But also, because the 4s orbitals, they are having an energy almost equal to the 3d orbitals, so we can say that the energy of the 3d orbitals is also equivalent to, almost equal to the 4s and the 4p orbitals. So the hybridization, because this involves the mixing of the orbitals which are almost equal in energy, so we can have hybridization of 3s, 3p and 3d. Also, in the process of hybridization, we can have the mixing of these three types of orbitals: the 3d, the 4s and the 4p orbitals. When it is going to be the mixing of the 3s, the 3p and the 3d orbitals, the hybridization names will be in accordance with s, p3 and d. Okay, so sp3 and the d orbitals, they can be 1, 2, 3 in number. So according to that, we will be having sp3d type of hybridization, sp3d2 type of hybridization, sp3d3 type of hybridization. And also, because the d orbitals, they are almost equal to 4s in energy levels, so we can get them also involved. So it can be a hybridization where there is d sp2, d sp3 type of hybridizations which are also seen. So when we have the d written after sp3, this means that the orbitals will be of the same principal quantum number. When we have the d written before s and p, this means that it is the d orbital of the penultimate shell which are involved in hybridization. Another thing about this dsp2, dsp3 type of hybridization, this is something that we will not be discussing in class 11th, because this is a part of your curriculum of class 12th. In the course called as coordination compounds, we will be discussing this type of hybridization, but not now. So here we will be discussing the hybridization involving d orbitals, where we have the mixing of the orbitals of the same shell, that is the valence shell of the atom. Okay, one thing more that you have to remember so that you do not confuse yourselves, the difference in the energies of the 3p and the 4s orbitals is quite significant. We will never be seeing a filling of the 3p, 4s and 4d orbitals. So it is never going to be, you can say, you can confuse yourself that this is also s, p and d being mixed. So this can be also a SP3d type of hybridization and so on, but no, because the energies of the 3p and the 4s orbitals, they are quite significantly different. So there will be never a mixing of 3p, 3d and 4s orbitals. It will be always 3s, 3p, 3d, or it can be 3d, 4s and 4p. So this is something that I really wanted to impress upon so that you never make a mistake about this. So now let us study about the SP3d hybridization. So as the name suggests, we have 5 orbitals, 1s, 3p and 1d orbital, which are going to mix with each other and they are going to be available for hybridization, and as a result we will be getting 5 sp3d hybrid orbitals. And because these is going to be equivalent to the VSEPR theory with the 5 electron pairs, we have 5 electron rich density areas, so this is going to be just having the same symmetry, the same geometry like we had for the 5 electron pairs. So it is going to be a trigonal bipyramidal geometry, and we have already seen this example in the VSEPR theory also, the formation of the PCl5 molecule. We will be discussing the hybridization also for this molecule. Okay, so what do we have? The geometry for sp3d hybridization, it is going to be a trigonal bipyramidal geometry. So diagrammatically showing, there is one s, one px, one py, one pz orbitals, and these are now going to combine with one of the 5d orbitals, and that d orbital which is participating in sp3d hybridization is dz square orbital. Now one thing more that you have to remember over here is that the p orbitals, they are identical in shape, they are identical in energy. So when we discuss a sp or sp2 type of hybridization where only one or two of the p orbitals they participate, it can be either of them. Okay, because they are similar in energy, they are equivalent in shape, so they can be any. It is only by convention that we first of all start with pz so that all of us can similarly think on the same lines. The textbooks study becomes easy and the confusion is not created. Otherwise these three orbitals, they are identical in shape, and the s orbital can combine with any of the 3p orbitals for sp hybridization, any of the 2p orbitals for sp2 type of hybridization. Okay, but when we consider the d orbitals, they are 5 in number and there is a slight difference in their energies. Okay, this difference in energy is something again you will be studying in class 12th in the course coordination compounds. There we will be discussing about all this in quite a great detail. We have a theory related to this difference in energies of the d orbitals, but for now in class 11th what you have to remember is that there is a difference in energies. So you have to remember what type of d orbital is participating in hybridization. So in sp3d hybridization we have the dz square orbital which is participating in hybridization. Okay, now when these are going to participate in hybridization, we are going to get 5 new orbitals, and these 5 new orbitals, they are the sp3d hybrid orbitals. And they are now how they are arranged. Well, the three orbitals, they are arranged on the equatorial plane on the three corners of a triangle that you can see over here, and this is going to give us a trigonal planar structure for these three orbitals. And these two orbitals, they are perpendicular to the equatorial plane, so we will be getting one pyramid joining this point to these points or the corners of these hybrid orbitals. So you will be getting one pyramid above and one pyramid below. So you now can see that we have a triangular base between the two pyramids that are formed. So this is why this is called as a trigonal bipyramidal geometry. Okay, and now if you see the angles, so because we have studied in the trigonal planar geometry, the angles were 120 degree between these. So it is similarly over here, these three orbitals which are on the equatorial plane forming the three corners of a triangle, their angle is going to be 120 degree, and these two orbitals, okay, so they are perpendicular to them, so this will be forming a 90 degree angle with the equatorial plane. I hope this is clear. These are the three equatorial hybrid orbitals and these are the two axial hybrid orbitals. One is above the equatorial plane and the other is below the equatorial plane. Now, one thing which can come into your mind is that why is there a difference in angles? When we considered the SP, SP2, SP3 hybrid orbitals, when we were not considering the lone pair of electrons, all the hybrid orbitals, they were at an equal angle, right? In SP3 hybridization, we saw that the angles were 120 degree. In in SP2 hybridization, we saw that the angles were 120 degree. In SP3 hybridization, we saw all the angles were 109 degree and 28 minutes. Now, why is that happened that these three are at an angle of 120 and these two at an angle of 90 degree? In the VSEPR theory, how we understood this was so that to have a minimum repulsion, this was the best position possible. Now, but based on the hybridization, we can explain it in another way also, and hybridization is a conceptual topic, right? It is essentially trying to explain the structures which were already known to the scientists. Okay, so the scientists knew that the structure is going to be this and they had to provide an explanation. So that is how Pauling explained these structures on the basis of hybridization. So what happens over here in SP3d hybridization is that it is not that is all five orbitals they are going to mix together. Okay, so the reason given for these different types of hybrid orbitals, 3 at an angle of 120 and 2 at an angle of 90 degree, is because that these all, they were not mixing together with each other, and they suggested that the S and 2p orbitals, they mix together, and these two orbitals, the pz and the dz square, they are mixing together. Again, we are saying a pz is mixing with the dz square. This is just a conceptual thing, and we are just saying it so because this is the orientation of these two are the similar ones. Okay, so that is why just we are saying that the pz is going to mix with the dz square orbital and these are going to mix with each other. So when S and 2p orbitals, they are going to mix with each other, we will get what hybridization? We will get SP2 hybridization, and SP2 hybridization, 3 orbitals mixing, and they are giving us 3 new hybrid orbitals, and these are the 3 hybrid orbitals placed on the equatorial plane. And then this orbital and this orbital, they will mix with each other. They do not have any s orbital contribution. It is only a p and a d, and that is why we are not seeing it on the equatorial plane. We are seeing it on the axial position. Okay, so I hope this thing is clear. Why do we have this type of structure in the SP3d hybridization? We have a mixing of S and 2p orbitals giving us these 3 orbitals, and these 2 giving us a axial hybrid orbitals. So they will be similar in nature and these 3 will be similar in nature, right? Now, if you have understood this thing, so you will be able to appreciate all the differences also that are seen. We will be discussing more about this in a lecture called as Ben's rule, where we will be understanding these applications of these type of orbitals more in detail. But for now, I hope you can understand that we have a mixing of 5 orbitals in SP3d hybrid orbitals. We will be calling all of them SP3d. It is only a visualization why we have these 3 to be different from these 2, by an explanation of this way that these 3 are mixing together and these are mixing together. So let us consider the formation of the PCl5 molecule now, and I think this is going to be very easy for you. Phosphorus in the ground state, this has an electronic configuration of 3s2 and 3p3. So we have 3 half-filled orbitals. No, we need 5 to make 5 bonds with the chlorine atom. So 1 is going to move from the 3s orbital to the vacant 3d orbital. In the excited state, we will be having 5 half-filled orbitals, and these 5 filled orbitals, they can overlap with the p orbitals of the chlorine atoms, and we will as a result form this 5 PCl sigma bonds, right? So I hope this much is clear. So the 3 PCl bonds, they will be lying in one plane and they will be at an angle of 120 degree, because this was the position of the 3 hybrid orbitals of the phosphorus atom. Okay, so phosphorus was having one sp3d orbital here, one here and one here, and on the overlapping we have the PCl bond. So these 3 bonds, they will be on the equatorial plane at an angle of 120 degree, and they will be called as the equatorial bonds. And then you can see that they will be the remaining 2 PCl bonds, one lying above the plane and one lying below the plane. They will be making an angle of 90 degree, and these will be called as the axial bonds. So this is making an angle of 90 degree, this is also making an angle of 90 degree, and these are the axial bonds. And the symmetry we have got is the trigonal bipyramidal geometry for the molecule. Now, one thing that you have to remember, this is something very important, that the axial bonds, right, they are at an angle of 90 degree through 3 bond pairs, right? So these 3, they are going to give it a high level of repulsion. So as a result, what we see is that the axial bonds, they are slightly longer, so that there is a longer orbital to accommodate the electrons, and it can have a minimum repulsion. So these axial bonds, they are longer as compared to the equatorial bonds, and this is what makes the PCl5 molecule more reactive. These bonds, they are longer, and these can be therefore broken easily, and if they can be broken easily, what we will be getting from PCl5 molecule will be PCl5 will dissociate to form PCl3 plus Cl2. And which are the bonds which will be broken? It is these 2 axial bonds which can be broken. We will be discussing again this about in more detail, more understanding about in the Ben's rule lecture. So please do be with me for that lecture for a thorough understanding on this concept. So now we have a few more examples of the sp3 hybridization, where they are now being involved the lone pair of electrons as well. So what you will have to again see is that how many electron density are there around the central atom, and if they are going to be 5 in number, we will be having sp3d hybridization. So the first example here we have is the SF4 molecule. So around sulfur, there are 4 bonds formed between the sulfur and the fluorine atom. So we have 4 sigma bonds and 1 lone pair of electron for the sulfur atom. So it is essentially 5 electron density areas. So we will be seeing a trigonal bipyramidal geometry for the molecule. And when we consider the shape, well, the shape is going to be dependent upon the position of the atoms only. So right, so we have the sulfur in the center. There is a wedge being formed below. This is going to be a seesaw being formed. The 2 fluorine atoms, they are swinging on the seesaw, right? So we have a seesaw formation for the SF4 molecule. There is 1 lone pair present, and this lone pair is always present on the equatorial bond. Okay, so the equatorial position for this lone pair again can be explained on the basis of the Benz rule. So please, I again request you all that do not miss that lecture. That will be really important for your conceptual knowledge. And then we have the ClF3 molecule. Again, we have two lone pair of electrons. These two lone pair of electrons, they will occupy the equatorial position and not the axial position, and this also you will be getting an answer in the lecture on the Benz rule. So we have again 5 electron density areas. 5 electron density areas means the geometry is going to be trigonal bipyramidal, but the shape you can see is like a T, so it is a T-shaped molecule. And then we have the I3 negative ion. So I3 negative iodine in the center with 3 electron pairs, which are lone pair of electrons and 2 bonded pair of electrons. So 5 regions of electron density. So we have trigonal bipyramidal geometry for the I3 negative ion, and if we consider the shape of the ion, it is a linear shape. Okay, all the 3 lone pairs, they will be occupying the equatorial position. So that would be all for this lecture. The next lecture we will be continuing the discussion further on the types of hybridization involving d orbitals. We will be discussing the SP3d and the SP3d hybridization. So please be with me for the lecture. Do subscribe to the channel so that you do not miss any lecture. Also click on the bell icon. You will be getting a notification immediately as we put up the new lecture. Any doubts, most welcome. Put that in the comment section. Mail us at h2ochemistry@gmail.com. We also have a Facebook page with us by the name of H2Chemistry. You can even log on to that, put up your queries over there as well. We believe in clearing all your doubts, so they are always welcome, so that your concepts are clear and you can clear your examinations with the flying colors. Okay, and then if you've liked this lecture, please do not leave without clicking on the like link. That is the real motivation for us to prepare more lectures for you. See you again. Have a nice day. God bless you.